Physical Science Period 3. I'm your host, Joel Shindell. Hot dog, we got an out-of-sight class today. Transverse and longitudinal waves. We're going to be doing some stuff in the hallways with the springs, so that won't show up on the record. The other day, though, we took a look at these vocab words. First of all, pulse. And a pulse is just one signal, kind of the crest or a trough of a wave. Half of a wave like one hum or one stroke. A transverse pulse is when the amplitude is perpendicular to the direction of motion. So in this example here, I've got it going left to right. Perpendicular means 90 degrees. It bumps up or down. That's 90 degrees. That's perpendicular. A longitudinal pulse is where you compress the spring. And then the stretch region is called the rarefaction. Okay? That's probably, this whole thing, the word rarefaction is totally new. Longitudinal, you've probably heard of. Where have you heard of longitudinal lines? Long. No? On the globe? Lines of longitude? So you've heard of that word, but not used this one. So remember, longitudinal pulses go in the direction of motion. They go back and forth. We'll see that. That's hard to see that because these ones move really fast. Okay. So what we're doing, that's from the other day, so you have those. Is we're going to go out into the hallway and we're going to reflect on this stuff. I'll take the sheet out there, and then we're going to come back and we'll finish this off. We'll make notes after we observe some. So I'm going to get a couple of springs set up, and we're going to just quietly out in the hallway. Line up. Okay, we just did this, and people are drawing in that if you have a fixed end, somebody's holding on to the end of the spring, this pulse comes in, hits the end, it returns on the opposite side. I'm just recording this. When I did this in the stairwell and nobody was holding on to that spring, the pulse is positive, up, right, it returns on the exact same side. So when it's a free end, that's represented, you can see there's a loop on a stick, right? That's how it's returned. Same side. This is important. Let's see some things about this. Other things. Okay, everybody's cool with the diagrams? Okay, let's talk through this, and you guys can jot down. I've already talked through these, actually, as you demonstrate. But what determines the amplitude, the amount of the hump size of the transverse pulse? We won't talk about the longitudinal pulse because you couldn't see it, but it's basically how much I squeezed in. But what about the transverse pulse? What was it when Jordan sent it? How much energy he puts in. Yeah, and basically how wide he moved his hand and how quickly he did it too. You do it slow, back and forth, it'll be a wide, fat pulse. If you do it really quick, it's going to be a skinnier pulse. And it's basically how you move, how wide you move your hand and how quickly. You guys jot those things down? Okay. You can just use your own words or whatever. Yeah, you can do it right on the sheet. So I'll pause. So we talked about number 2, and you guys came up with it. Does the pulse change shape as it moves in the spring? Yes, it gets smaller in size. So what causes that change? It does. It gets smaller in size. Why did we say it gets smaller? Friction. Yeah. Is what basically, remember when we lifted it off the floor, it went back and forth like 5 or 6 times, right? Less friction. It goes. Yeah. Friction is why it's reducing in size as it goes.
I'll talk to you about an isolated system after, but we're not going to be too worried about that. Okay, recording now. Would you expect the pulse to change shape if this was an isolated system? What's meant by an isolated system? That's if we could somehow have zero friction. Do you think, from what you saw when we lifted it, I think it was you, Jesse, and I? Yeah, we lifted it. There was less friction. What'd you notice? Did it change shape as much? No. So if it was an isolated system, that means there was no other forces acting on it, friction forces. There's no gravity acting on it. If you were to do this in deep space, it should go back and forth forever, really, right? It's only because of friction. So the pulse would not change shape if you had no other forces acting on it. It would just go forever, back and forth, back and forth. That's what the last bit of number 2 is talking. Third point, how is the reflected pulse different from the incident pulse? The incident pulse is the one that's sent, reflected, I think you understand, it hits the end and comes back, reflection. What happens? We have this refer to diagram, basically, right? It comes back, if it's a fixed end, it comes back on the same side. Just say refer to diagram, because you have it down there, right? If it was a free end, it came back on the same side.
Just write refer to diagram.
Just write refer to diagram, because you have, I think the diagram explains it better than words, don't you? Probably.
I don't like words anyway.
You're an actor. You should love words. 4 and 5 will kind of do together, because it really get it at the same time. Describe the motion of a strip of tape. We didn't actually have one, but I think you could imagine. As the spring, in the middle of the spring, as the pulse passes, let the tape move in the direction of the pulse. What happened to the tape? Oh, we didn't have tape, but what happened to one spot on the spring? It just went up and then down, right? It's, what's the magic word for 90 degrees? Perpendicular, right? To describe the motion of the strip of tape at the middle of the spring, it just went back and forth. It moved perpendicular to the pulse. If you want to do a little mini diagram, you can do that too. 90 degrees perpendicular. I want you to know the word. I'll be using it. That's how the medium works, right? So 4 and 5 are really the same aspect of looking at it. The particles don't move with the actual pump, the pulse. They just move up and down or sideways. Remember when you're doing the wave across a crowd, you stand up in your seat, put your hands up, you sit back down. You don't move left or right. But the illusion is that something is moving. It's not matter. It's energy that's moving from left to right. Okay? What we just saw is, if this pulse is 1 high, that pulse is 1 high, they double up. 1 plus 1 is 2. So I would suggest that you draw the middle here during the interference, we call it. The pulse would double. It's the 2 pulses added together. That's interfering with each other. But then a moment later, they pass through. And this is why I color-coded mine. I don't care if you have 2 pens. You can't color code. But the red one then passes through back to the same side. The blue one passes through back to the same side. Untouched. Cut. Other than friction. Does that make sense? That's kind of what we saw. Okay, I'm going to talk to you about something underneath where it's written on paper. So, superposition. Principle of superposition is the resulting amplitude, the size of the hum, of 2 waves, interfering waves, is the sum. And this is like adding integers. 2 positives add to make a positive. Constructive interference occurs when wave displacements are in the same direction. Now, yeah,
I had done the same thing, and instead of on the left side, I did two hops approaching each other on this side. What's going to happen? They'll still add together. So two negatives add to be -1 and -1, add to be -2. So during the interference part, it would have been big like that, and then they just pass through afterwards, right? It works the same way. Positives add together, two negatives add together and make something larger. That's called constructive, building, right? Construction. Curves and displacements are in the same side, same direction. Two positives, two negatives. The result is a wave that has an amplitude greater than those of the individual. You can add it. A larger pulse appears when two wave crests, or, like I said, if they were down below, two forms. The point where maximum amplitude occurs is called the antinode. I'm going to get you to just underline that antinode to the double hump or the built up. It doesn't have to be double. It's one could be size of 1, the other one could be 10 centimeters, and the other one could be 20 centimeters. They're not equal. They'd add to 30 centimeters. It's mathematically add. Now, we're going to use the word antinode. You better know what's the first. Yes, the answer. When a crest and a trough meet, we notice it flattened out. So now, for Estelle and I to do this perfectly, we would have had to have the exact same amplitude, and then it would flatten out perfectly. But it's hard to arrange that. But what we saw was the red and the blue came to kind of flatten each other out. So I just made a big, like it's flat, more or less. More or less, right? After they meet, though, recall they sailed right through each other. The red kept going that way, unaffected afterwards. Blue kept going this way. Just follow that, right? That's what we saw. I mentioned something before we finish this part off. If I had one coming in, I'll just disappear. That had a height of 2, and this one had a height of -1. How would they meet in the middle? Mathematically, 2 and -1, they would come together and form something that was just one high, right? And then they'd keep passing each other, okay? Does that make sense? So it's just that it's like adding integers in grade 6. Now, I've rewritten, this is the same principle as superposition from before. True interference is the sum of, this is the sum of positives and negatives. Now this time it makes sense. The other's constructive when it builds higher. Destructive is, well, destroy, right? Come down, it flattens it out. It occurs when wave displacements are in the opposite direction. So if you have an amplitude that's less than those of the individual, it might even flatten out if they're exactly equal and opposite. And when the pulses of equal and opposite amplitudes meet, the displacement is 0. And what you want to place is, well, there's antinodes when they build. These are nodes when they flatten.
That's the during interference.
No motion occurs. And I was just going to zip up to the middle diagram, say this is our node. All right. Exactly what you were getting at. Perfect. We're going to read this together, this example. You can do the work right on the sheet. And for some reason, when I sent to the copier, you notice there's a stapled sheet with nothing on it other than Pearson. Okay, that shouldn't have been there, but keep it on there. You can do your work for the numbered problems later on there. But do the example right on this page, okay? We'll work together. Let's read it carefully. Create a fixed pulse in an ideal spring. Ideal spring means it's actually really good. No kinks in it, no friction. Move your hand sideways, a distance of 45 centimeters. So here's the spring, and you went up, down. That up, down was 45 centimeters, right? I guess I'll get rid of, I want this to, so I don't want these. That was 45 centimeters. Okay, and you're sending that through from the middle position, the equilibrium position. It takes 0.8 seconds from the time you begin to move your hand until it returns to the spring. So that's how long it went back and forth. Remember how when I was saying, or I saw, or whoever, like, you do it faster, then it's a skinnier hump, right? If you do it slow, like you take a full second or 0.8, 80% of a second, it's going to be a pretty wide hump. If the pulse moves at a speed of 2.5 meters per second, so I'm going to say that's my velocity, speed, but we use it. You calculate the length of the pulse. Now, do you remember when you do it slow? So if you take a full second, what does the pulse look like? It's wide. Okay? It'll be like this wide. If I had, instead of 0.8 seconds, if I had done it in 0.2 seconds. Wait. Now, what I was saying is that what if I flicked it faster, 0.2 seconds for the up down? Then the pulse would be the same height, but it would be skinny. Does that make sense? We're wondering how wide because it was done so slow. That's why 8 of a second. 1 second is kind of long. So, what affected the speed of the spring? You guys remember? It wasn't how, no, it wasn't that. Remember a short, the tension on the spring, yeah, how tight it was. If we were close together, it was looser, and things moved slower. So it's actually the medium that determines, not how hard you flick. So that 2.5 meters per second is whether you do a 45 centimeter flick, a 20 centimeter flick, or whatever, right? It's still going to be 2.5. And it doesn't matter how long it took you to flick it. It's still 2.5 moving from left to right on the pulse. Okay. Calculate the length of the pulse described. So we need V, T, and D in one formula. You guys remember from grade 8 and stuff? Okay. What's the speed limit out in front of the school? 30 what? 30 kilometers. No, that's different. Kilometers per hour. Now I ask you this because speeds, highway speed 110 kilometers per hour. That's kilometers distance over time. Hours. If you remember that, then you know the speed formula is V is equal to D over T. Kilometers per hour. Well, in this case, we're going to use meters and seconds. Hours, seconds, they're still time. We're trying to find the D. Do you guys find it easier to put the numbers in and then find D, or do you like to find D with the variables and then put the numbers? Numbers first. Okay, we'll do numbers. So I've got 2.5 meters per second for the V. I'm going to replace it. I like using flat fractions, and you'll see why. The way I do it. They're canceling out. And the time is 0.8 seconds. Now it's important that I'm putting 80 because that means it wasn't just 0.8 give or take. It was 0.80. It was like measured on there. It might have been 0.7999, but I mean it's very close to 0.80. I'm confident.
Is this your question one?
This is the example. Oh, the one that was underlining things on? Okay. Mathematically, now don't worry about the meters per second and the second for the moment. How do I solve for the letter D algebra? I want to get it alone. It's already on the top. What do? Times up the decimal 8 on both sides. Right? It cancels. I'm not going to write this down off as it'll disappear. Oh crap, it won't. No.
Because you have that one covered.
0.8. I'll just do it like this, and then 0.8. This is what I'm thinking. And I'll just write this down. You know how it cancels here and here, and that's the way it works? Well, I'm gonna write this down though. I'm gonna just put the 0.80 seconds times the 2.5 meters per second equals D. Now that's a calculator issue, right? Also though, here's why I like the flat fractions. You want to slash fraction fine, but meters per second and seconds are the units. What happens to the seconds on the top? 1.80 seconds. And the seconds on the bottom? Algebra. X on the top, X on the bottom, what happens? You cancel. I heard cancel, not too constant. You're left with meters, which is what you want. You want to tell them why it is. It's 0.8 times 2.5. You guys got calculators. You can't do it in your head. What is it? I'm going to flip-flop the D to the left. 2.0 meters. That's a pretty darn big hump. But this is what we figured out. This meters wide. How tall would the hump be, actually? What's the amplitude? That is the 45. Wasn't it 45? I think it was. Yeah, 45 centimeters. The amplitude is 45 centimeters. So this is definitely not drawn to scale. It's short and fast. Okay, you guys, talk to you tomorrow. We'll do calculation stuff together tomorrow. I will pause this first.